The chapter we're starting today, you guys, chapter 8 is all about the normal distribution. Okay, so it's a bell-shaped curve. We're going to talk more about it in our next lesson. But some of you in this chapter, depending on what math class you came from, could have seen some of this stuff before. Okay, so if it looks familiar, that's great. I'm going to teach it like you've never seen it before. But if it looks familiar, that's why. Depending on the math class you came from, you could have had a little bit of statistics in that math class, and it would be from this chapter. So here we go. Today we're going to start off with talking about standardized scores, which are otherwise known as z-scores. It says, in sports, it's difficult to determine which player is a more valuable asset to their team because players play different positions. So, for example, for soccer, you guys, if you're trying to decide between two players to be your MVP, is it your forward who averages 1.3 goals per game, or is it your goalie who averages 5.2 saves per game? Their jobs are to do two completely different things. So how do you measure who's the better player, who's the most valuable player to your team? Okay, and one way to do that is to use a standardized score or a z-score. You guys, a standardized score, or more commonly known as a z-score, measures how many standard deviations a performance is above or below the mean. Measures how many standard deviations a performance is above or below the mean. And remember, another word for mean is average. So the z-score formula. Z equals the performance minus the mean divided by the standard deviation, because it tells you how many standard deviations it is. So you find the difference between the performance and the mean, the numerator, and divide by the standard deviation. You are absolutely going to need to know this for your test, you guys, this formula, but we're going to do so many problems that involve z-scores, you'll have it memorized in no time. Okay. Quarterbacks in the NFL love to complete passes, especially when the receiver scores a touchdown. However, passing comes with a risk. The defense could intercept the ball for a turnover. So we have data here for Aaron Rodgers' performance in 2009 for two different variables, his touchdowns per game and his interceptions per game. It says, calculate Rodgers' z-score for touchdowns per game and interpret this score. So we're going to be looking at this column right here. So z-score formula from up top, z equals x. So how he actually did, Rodgers' performance, 1.88 minus the average for the league, 1.35, divided by the standard deviation. Whoops, sorry, plug in the value for standard deviation, which is 0.49. Okay. When you enter this in your calculator, you guys, you can enter it all in at once. That's fine, but make sure you have parentheses around your numerator. You don't have to enter it all at once. You could just do 1.88 minus 1.35, enter, and then divide that by 0.49. Okay, but if you do want to enter it all in at once, you got to put parentheses around that numerator. So if we round to the nearest hundredth, 1.08. Phones away, please. So that's how we're going to round our z-scores to the nearest hundredth, 2 decimal places. So it's a positive z-score. So that meant they were that many standard deviations above the mean since it's a positive z-score. So interpret this z-score. What does it mean? Rodgers' touchdown performance was 1.08 standard deviations above the mean. If that was a negative number, you would say he was 1.08 standard deviations below the mean. Always in your interpretation, report the z-score as positive, and the words above and below determine whether or not the performance was below average or above average, okay? Now we're gonna look at interceptions per game. That's this one, the other column. So find the z-score, use the same formulas up top. Z equals the performance for Rogers was 0.44 minus the mean 0.95 divided by the standard deviation. Type it in, see what you get. Remember, round to the 100th, 2 decimals. Negative 1.34. So Rogers' interception performance was 1.34 standard deviations below the mean. Next question. Relative to the other quarterbacks in 2009, which of his performances was better? His touchdowns per game or his interceptions? Now, look, I know this one up here is higher than this one. However, interceptions are turnovers. They're bad. They're not good, okay? You want to be below average for interceptions. While touchdowns, they're a good thing. You want to be above average. So which one is actually the better performance relative to other quarterbacks? It's going to be the interceptions performance. Notice, remember what I said, this is bad, it's not good. So you actually want to be below average. So this is 1.34 standard deviations from the average, while this one's only 1.08 standard deviations from the average. So why? Because it's further away from the average or the mean. Questions at all on the front? Okay. Okay, I'm going to grab a couple of different highlighters for this one. Okay, we have lots of data here. It says, I guess we just started baseball season, Major League Baseball season, so here we go. The single season home run record for Major League Baseball has been improved just 3 times since Babe Ruth hit 60 home runs in 1927. So, Babe Ruth hit 60 home runs in 1927. Then, it wasn't until 1961 where Roger Maris beat that record with 61 home runs. And then Mark McGwire in 1998 hit 70 home runs. And then Barry Bonds hit 73 in 2001. Just trying to separate all that information. So by just looking at the totals, it appears, you know what? Barry Bonds is the best home run hitter because he hit more home runs than any other player. So he's the best, right? However, baseball historians, you guys, feel like it's easier to hit a home run in Major League Baseball nowadays than it was back then because of factors such as quality of the batters, the pitchers, dimensions of the ballparks, and something known as performance-enhancing drugs. Okay, so they're saying, you know what? Barry Bonds isn't necessarily the best because it's easier to hit a home run nowadays than it was back in the day. So, here's the data for each year. So we have 1927, if you want to try and follow, 1961, 1998, and 2001. So here is the corresponding mean and standard deviation for each of those years that the record's been broken. Before we get into overall, which player do you think had the best performance? It says distributions for each year were all skewed to the right. Now, one thing up here, you guys, it says when comparing z-scores, it's important that the distributions are roughly the same shape. Doesn't matter as long as they're the same shape. So they're saying all the distributions were roughly skewed to the right. Why do you suppose that is true? So just to remind you guys, skewed right looks something like this. And maybe with an outlier or two at the end, okay? Remember, skewed right. So in a skewed right distribution, there's outliers or potential outliers at the upper end. I would think that all of these players up here, yeah, they're that potential outlier or that outlier at the upper end of the data set. So why do I think the data is skewed right? Why am I not surprised by that? Well, because there's few exceptional performances. Okay, there's going to be more performances around average or below average. In the middle or lower end of the data set. Okay, this up here, it's your Babe Ruth, your Roger Maris, your Barry Bonds. Okay, it says use the table above to find the standardized score. Remember, standardized score is just a fancy word for z-score. For each of the 4 players. So divide part B into kind of 4 parts. I want you to find the z-score for Babe Ruth, the z-score for Roger Maris, the z-score for Mark McGwire, and Mr. Barry Bonds. Remember, if you need to, I'll rewrite the formula up here for z-scores. Z equals x minus the mean divided by the standard deviation. Round to the 100th, guys. 2 decimal places. Round to the 100th. Go ahead, find each z-score. Okay, check your answers to the 4 z-scores. Remember, round to the 100th, 2 decimals. I put about because it's approximate, because we rounded. You don't have to have about in your work. Okay, it says, based on the standardized scores above, which player had the best performance and why? Probably, hopefully, you're going to be going with Babe Ruth. Couple of reasonings you could have given me. Simply, Babe Ruth's got the highest Z-score. And with home run averages, I want to be above the average. You guys, 90% of the time, you want to be above average. Be careful, because I give you a lot of sports examples in this class, you got to be careful with timed sports. So when you're talking timed sports, you're talking running, track, and swimming, right? Because for any timed events, do you want to be above average or below average time? You want to be below, right? So be careful. Although 90% of the time we want a high Z-score. If I were to give you all your scores for yesterday's test in terms of Z-scores, you're hoping for the highest score. You're hoping for the highest Z-score because you want to be above average on the test, right? A lot of times we want to be above average, but be careful. About 10% of the time you want to be below, okay? And be careful with anything that's timed. Ruth had the highest Z-score. Okay, or you could say Ruth was more standard deviations above the mean. Okay, this next one. If the Z-score of a particular player in 1998 was 2.7. So they're telling you Z was 2.7. About how many home runs did that player hit that season? Okay, I'm still going to use my Z-score formula, but I'm just solving for a different variable here. I know the Z-score is 2.7, so I'm going to plug that in. Equals, I want to know how many home runs the player hit that season, so I'm solving for X minus, now it's from 98, so go back and look. The mean for 98 was 20.7, the standard deviation for 98 was 12.7. Okay, guys, good old algebra. So you have to ask yourself, how do I solve for X? Multiply both sides by 12.7. So the 12.7s cancel over here. So what is 12.7 times 2.7? 34.29. Equals, what am I left with on the right? X minus 20.7. I want to get X by itself, so I'm going to add 20.7 each side. So X is right about, what do you think you're going to write for your answer? 55 home runs. Okay, the reason why it didn't come out to be exactly 55 is because your mean and your standard deviation were rounded numbers. Okay? We got one more page. Questions? Okay. You guys, there's a little information about fantasy sports, and a lot of times it's cool that you can use Z-scores to try and figure out who would be the better player, like I said, relative to their position. But I'm going to jump in right into the swimming and diving example. So swimming and diving is a sport in which whether a positive or negative Z-score is more favorable depends on the event. In swimming events, they're timed events. A better score consists on being more standard deviations below the mean, resulting in, if you're more standard deviations below the mean, you're resulting in a negative Z-score. Or we could say, hopefully, a low Z-score, right? With diving events, you guys, for a diving event, you get a score out of 10. So do you think you want to be above average in your diving scores? You do. So with diving events, players are given a score from 0 to 10. Therefore, an athlete would want to be more standard deviations above the mean, so they'd want a positive Z-score. Or in other words, a high Z-score. So let's see here. For swimming, we want negative Z-scores, okay? However, for diving, we want positive. Okay, this means to find the overall, so for fantasy scores, you guys, they combine multiple variables and put them all together, okay? So it's just like if you play any sport, it's not just one thing you're trying to do well. Hopefully you're trying to do a few things well. Maybe if soccer, if you're the forward, you're trying to score goals, if you're trying to get assists. Do you see what I'm saying? There's multiple variables. So then this means to find the overall fantasy score, we would add values where a higher z-score is better and subtract values when a lower z-score is better. This way, if you subtract a negative z-score, it results in a positive, and so you're getting a better overall score. Okay, so we have data on Amanda, who's a swimmer, okay? She performed in her meet, let's say, she performed in these 4 events. And based on her performance, mean and standard deviation, these are the corresponding z-scores. Okay? Remember, this is a swimming event, so we actually would want a low z-score. Low z-score is better. Okay? Another swimming event, you would actually want a low z-score is better. Again, a low z-score is better because this is also a swimming event. And this last one is a diving event where actually a positive z-score would be better. So the first question says, interpret Amanda's z-score from the 200-yard freestyle event. Okay, try this, take a minute, try this on your own. Her z-score from the 200-yard freestyle is negative 1.09. So go ahead, take a minute and try and interpret that. That's from the front. If you need to, look back at the front of your notes. Okay, when you get a second, check your work. Make sure you said, again, we always report the z-score as positive, and the fact that the z-score here is negative, we indicate that with the word below. So Amanda's 200-yard freestyle performance was 1.09 standard deviations below the mean. Okay, this last one, you guys, is kind of like what you're going to have to do in your homework number 5. The judges want to give the MVP to the athlete with the highest overall combined scores. Combine Amanda's 4 z-scores to determine her overall score. So, remember, the first 3 a low z-score is better. So we're going to subtract values where a lower z-score is better. So it's going to be minus a negative 1.09, because remember, that will turn a positive, that's a good thing, minus 0.4, because a low z-score is better, minus a negative 0.95, that's good, that's below average, it's going to turn a positive. However, the front dive didn't do as well, and she actually wants a positive z-score is better. We add z-scores where a positive z-score is better, so plus a negative 0.28. Remember, the double negatives turn to positives. If you combine those all together, her overall score would be 1.36. I think this one's a little trickier than the one in your homework because we want so many negative z-scores because there's so many timed events, while the one in your homework is you're combining ones where you want more positive z-scores and there's only one bad variable, the turnovers. Okay?